Uh, Let us start with the third module. So, after all the rigorous mathematics and kind of, I would say, a little monotonous discrete maths, now we are in a position to understand some of the applications of those in terms of the symmetric ciphers as well as the asymmetric cipher. I keep on telling you that the third and the fourth module will be very important for your CAT 2 as well as for your this whole course for that matter. These two modules, 3 and 4, forms the basis of cryptography and the techniques involved. And some of them have already been introduced in module 1. You will soon find that block ciphers, system symmetric ciphers, and all these are like it has been introduced already. But now the mathematics which we have learned in second module will be applied on top of it. And some of the cases we will find out that what are the principles of DES, the data encryption algorithm AES. This is the advance of DES. As well as you can see pseudo number generation. We have received last class only we have found that what exactly is pseudo number generation or the principles of pseudo number generation. And now we will find the methods of using it and how it has been used for the RSA. You can see RSA is there, public key cryptography. Euclidean, the elliptical curve algorithm that we have discussed, that also is applicable on RSA. So this forms, the 3 and the 4th module forms the basis of our discussion. All right. So keeping that in mind, let's start off. These are the sub-components of the module which we are going to discuss. So block ciphers, encryption standards, DES and AES, little tough I would say. This AES particularly, DES also is relatively easy because the key length is smaller, so it's relatively easier, but AES is a little tough I feel. But anyway, we'll see one by one how it goes. Then pseudo-random generation, stream ciphers and public key RSA. So these are the topics we need to cover. Let's see how much we can do it as much as possible. So first things first, which we already know is the stream cipher. If you remember, we had already discussed the stream cipher and particularly this particular diagram itself at the end, fag end of module 1 when we were discussing about the block ciphers and stream cipher. So stream cipher is basically where you have a stream of information or a message P and we have a cipher text which is C. The key will be K. And if you observe here, the K can be a predefined value or it can be a dynamically changing element. But the most important point is that here, each and every element or character or bit, whatever you call it, one by one it will be processed. If you observe over here, P is given by a set of P1, P2, P3. Each and every time C1, C2 and C3 is generated by some kind of an encoding algorithm EK1, where EK1 is the encoding algorithm specific to K1 applied on the bit P1. Similarly, we will have C2, C3 accordingly, and then we will combine together one by one, like for example here, this plain text over here, PLAIN, like that individually one by one the characters will be encrypted or ciphered and accordingly SO will like be in that way the cipher text will be generated. So stream cipher deals with one single bit or one single character or one at a time encryption if you call it that way. And in that way, if you observe the monoalphabetic and Vignay cipher, these were the two algorithms which, in fact, Vignay cipher we have discussed a lot, in fact. So these are some of the existing tools which you already know, in fact. Those are the stream ciphers as an example. Now we'll see that the modern stream cipher, modern block cipher, how it differs accordingly and why we are studying in the third module. Why not that we have already discussed it in module 1 and we are happy with that. Why we have to discuss it again now. We'll see that one by one. The next thing is the block cipher, the basic two categories, the stream cipher and the block cipher. In block cipher, what happens ideally, that there will be a block of data on which we are going to work on the encryption process. So if you observe here, the single key is used to encrypt the whole block, even if the key is made of multiple values. For example, the plain text over here has been divided into this manner. And then we are using some kind of an encryption using a single key, unlike to the K1, K2, K3 in the previous case. And finally, we are block by block. If you observe, this is a block, this is a block, like this is a block, like that, block by block, we are actually encrypting the whole setup. And if you remember, Playfair and Hill cipher, in both the cases, these are some of the examples of block cipher, early block ciphers, where basically a die bit were considered as a group, and we were trying to find out the pattern, we were trying to find out the combinations that were happening in the whole encryption process. Remember the Playfair and Hill cipher, that's what we are doing, right? So we were arranging the plain text with respect to a particular key. We were arranging a matrix in terms of Hill cipher. In Playfair, we were designing a matrix of 5 cross 5, but we were checking with 2 bit at a time, or die bit at a time. Now the point is, this is where the important slide comes in, that why we are actually discussing this here in third module. The significance of this particular module and why the importance is. You can see the traditional cipher, symmetric key ciphers that we have studied so far are character-oriented ciphers. We were encrypting a text. Okay, we are encrypting a sentence for that matter. But with the advent of computer, we needed bit-oriented ciphering, because the information can be of any form, like an graphics, like an audio or a video data. So basically, these are analog format. At times, initially it was analog format, which converted to digital format. But if digital data is there, naturally we will have 0 and 1 of different patterns of lakhs of data that we are handling with. In that case, this symmetric key cipher needs a modification. The conventional character-based ciphering is not suited for the requirement. So that is one of the case in terms of why we are studying here. Based on the mathematical tools which we have already discussed, we will try to use that for the bit pattern or for digital bit of data. It is convenient to convert this all types of data into a stream of bits to encrypt the stream and then send it to the encrypted system. Now, if you observe, in addition to this, with one of the advantage of using this, when text is treated as a bit level, each character is replaced by preferably 8 bits or 16 bits. We will consider mostly for our discussion as 8 bits, which means that the number of symbols becomes 8 or 16, and which is pretty a pretty high number, because there can be multiple combinations of symbols that is possible. That eventually what will happen, that when you are encrypting a data, encrypting a message, definitely you will have more possible combinations of encryption, and hence the security aspect will increase a lot. So that is one of the main motivation towards changing the algorithm in the way the bit stream works. Process is same. There will be a key, there will be a block of data, a chunk of message which will be taken one after the other. The key will be on top of it. We will encrypt the data and it will be sent to the receiver. The receiver will also have the same key. It will use some digital operation and it will retrieve back the message. The process is the same, except that we are going to use certain fundamental rules on top of the digital data. Okay, so that's the fundamental changes. So now we have a small difference between block and stream cipher. The block cipher processes the messages in block, which we have already understood, and stream is one by one. And if you observe that, like a substitution on very big character, that's basically what the block cipher does. And for example, stream cipher, it processes the bits or bytes at a time when during the encryption or decryption. So that's another thing. Many current ciphers are block ciphers, so that's why we are going to focus primarily on modern block ciphers technique for the time being. As time goes, we will discuss about the stream cipher also at a later stage. But initially, we are going to discuss about the modern block ciphers. Now, this is again just a diagram to understand the basic difference between the two. Already understood. So you can see the second one over here. This is basically a block cipher when there is a plain text of B number of bits. Okay, and we have a key which also will have certain amount of number of bits, and there will be some kind of an encryption algorithm where primarily you will find that we are going to do some kind of an XORing. Okay, that's a very, very basic and very commonly used digital operation or binary operation that will come across. And hence the ciphertext will also be generated, which will also have the same number of bits as that of the plain text. So the plain text and the ciphertext will have the same number of bits. On the other hand, if you observe the first half, this is basically stream cipher. Okay, in which the key which you have over here, it gets changed to something like a KI, because remember, we are doing it for per bit. Okay, per character, if you imagine that way. So basically, there will be some kind of a key generator matrix which will go on changing the key at a time, and that kth bit or the kth key will be used for the kth input bit. So that's why you can see the plain text also has pi over here. So P1 will be merged with Ki, P2 will be merged with K2, like that, so on and so forth. It's just a diagram to understand that. So now we come to modern block ciphers and the necessary information. Some of the informations are important, so please make a note of them when I'll tell you to. So symmetric key modern cipher encrypts an n-bit block plaintext. Please make this like the nomenclature with you. N-bit block plaintext decrypts n-bit ciphertext. So basically, you always the plaintext will be represented by small n. That's very important, and the k bit will be the key. All right, so that's how it is, and the process is already we have discussed about the block cipher, so we don't need to discuss that much. But two conditions we will check in the right hand side: if the message has fewer than n bits, okay, if the message has fewer than n bits, then padding is required. Padding must be added to make it n bit block. So if the message has fewer than n bits, if the message and the key has differences in the bits, then we suppose we have defined a block which has 64 bit. But suppose you are dividing it for a long bit stream, you are in a position where the bit stream is of 60 length. So you have to add 4 such padding bits to make it 64 in order to make the thing happen. It's very similar if you imagine that in case of Playfair as well as for Hill Cipher, whenever there was a redundant bit, we were adding up an X. Or suppose the example that we had given in your exam, what the cup in a cup or something, the last P didn't had anything as a die bit, so we had added Z or a X at the end, right? Those who did it properly. So that is basically a padding. You can imagine in that way. So whatever happens, the predefined structure was 2-bit at a time. So whatever happens, we have to make sure that 2-bit happens. In Playfair, I'm talking about. Here also the same thing is mentioned that if it is less than that, we need to do some kind of a padding. We'll give you an example how it is to be done in a digital format though. And second one is when message is greater than n bits, then it should be divided into such manner such that it becomes an n-bit block. N-bit again, you specify that what is your system, what is the requirement of the how many number of bits it can handle. So based on that, you make sure that if you have a longer or a larger data set, you break it up into smaller segment which will be equal to n bits. And in that case, if at all, in that also you require a padding, you can see appropriate padding must be added to the last block if necessary. If it is not required, if it is like everything, if the whole block is divided equally, then you don't need to do anything. We'll see that with an example also. But if it is not, then you have to add the requisite amount of padding. This padding, usually what happens for a block cipher, or in fact that is applicable to many of the other systems, this padding will always be done at the last block of the whole set. Suppose you have, just example, suppose you have 100 such 100 blocks of 3 bits pattern. 100 such block, 100, like 1, 2, 3 such block. Each block contains 3 bits. Okay, and there are 100 such blocks present. So the point is, this the padding part usually happens at the last block that we come across. Similar to PZ, if you remember in the example, we have added that Z at the end. Not that we have clubbed in somewhere in between to make that new bit come in, right? So same way, the last block is usually have the padding involved. And for most of the times, this padding is done by adding multiple zeros at the end. As we know that 0 doesn't have any much meaning for preferably. And if you analog wise, if you signal wise, if you imagine, this is just my interpretation, I'm just to make you understand. Like if you add more number of zeros, signal wise, what does 0 mean? Or if I give you a signal 0 and 5 volt, what does that interpret to digital system? 0 and 1. So where if you are adding up with ones, suppose you are padding up with ones, then basically you are applying some kind of a amplitude of a signal. Understood the analogy I'm talking about? But if you are adding 0, you are basically making sure that there is no such loss in the signal that you are doing. There is no power requirement. If you are sending a 0, it doesn't matter much. So that's why most of the time these paddings are zeros. Mostly. Okay, that's just a intuitive understanding. Now let's take an example of understanding how in terms of padding is used for our case. So say the question first, please make a note of it. How many padding bits must be added to a message of 100 characters if 8-bit ASCII is used for encoding and the block cipher accepts block of 64 bits? So this 64 bit is the limitation for us. Whatever be the number of size, 64 bit is the total number of bits per block that is available. So whatever happens, you have to make sure that it fits into that 64 bits. And if at all it doesn't fit, you have to either add padding or you have to do some modification. So that is what the question is. So let's see how it is to be done. So if you observe here that you have 100 characters and 8-bit is there. So one character is 8-bit as is mentioned over here. So we have total 800 bits that to take care of. Alright. Now if you observe here, the message bit is much greater than the bits that is provided for the block. The first case over here. Alright. So this message is greater than the n. So in what we have to do is we have to add an equation. So the equation is very simple. M mod. This mod indicates the length of M. So you can see M and this pad are length of the message and length of the padding. So basically you have a message. If I draw it this way, so this is what it's mentioned. So suppose this is my message and this is my padding. Alright, so this together should be of 64 almost. That's what the idea is. Like most of the time what will happen, the message will be added up with a padding if at all is required and to make it equivalent to the requisite amount. So now what you are looking at over here, you can see message plus pad is equal to 0 because the remainder is 0. Why remainder is 0? Because it is a uniform block. Suppose there is no requirement of padding. So generic equation is M plus pad is equal to 0 mod 64 because 64 is the bit that we have. Pad would always be, you can see M was 800, so minus 800 mod 64, mod minus 800 is not possible, so 32. So what does this mean? Okay, 32, that means that for 800 bits, you need to add up 32 bits of padding. As you can see, for example, all 32 zeros needed to be added to the message. So what was an 800 bit message? Now it will be called as 832 message. And if it is 832 messages, you can see there is a uniform distribution of 13 blocks of 64 bit each. And we are distributing it accordingly. Understand? So 800 bits was there. So we have added 32 bits and we have made it sure that the block cipher remains as it is intact. Because now the 832 bits will be divided into 13 such blocks. Each of those 13 blocks will be appended by some kind of a key K and the enciphering will be happening. The cipher text will be generated. At the end also we will have 832 bits. At the receiver we will understand that the last block will have the padding. So we will remove the padding over there and we will extract out the information out. Understood? So that's the logic behind padding. Okay. And one of the another advantage that padding usually does is not, it's mentioned over here or it's not related to cryptography. Usually what happens whenever you are sending a data in a transmission in a wireless system, the padding will help us in removing the unnecessary in ISI, the inter-symbol interferences to happen. Because suppose you have this as 64 block. This is another 64 block. Just imagine this way. These two 64 blocks will not be residing this way. While you are sending it in a wireless channel, this will overlap like this. That's the fundamental of wireless communication. So now when they are overlapping, you can imagine a portion of the data, which is this part, is basically getting lost. This zero padding will help us eliminating that. Because even if it overlaps, the overlapping length will be adjoined with the number of bits that you are appending. Hence, even if there is loss, the loss will happen with the padding, not with the data. So it's basically, the meaning is the padding encapsulates the data. It saves it from getting lost. These are the implications of it. It's not related to you, but just for your information, I thought of telling you because this has other significant information. So keeping that in mind, let's see if you can understand this and you can find your own answer for this. Question is, a message has 200 characters. If it is supposed to be encrypted using a block cipher of 64 bits, find the size of the padding and the number of blocks. Can you please do it and quickly and let me know what is the answer you are getting? Remember that one character is equal to 8 bits. That you can consider. A message has 2000 characters. If it is supposed to be encrypted using a 64-bit block cipher, 64-bit you will soon find that's like a standard in block ciphers most of the time. 64, and there is another one is 56-bit also. You will have a key size of 56. So that's the standard one. That's why 64 is used. Find the full size, find the size of the padding and the number of blocks required. Can you quickly use that equation m plus pad equivalent to 0 mod of 64 and find out that what are the things required? I'll keep this as a reference for you so that you can solve it. The previous example, I'm just keeping it for the reference. If you need the help, you can take this as an example, like a sample. The question is, here in this case, if you observe that we have 2000 such characters and we have that 16,000 odd bits. Now, if you have 16,000 odd bits, if you just substitute in the same manner to the equation, you are getting a remainder as 0, which means that you don't require any such padding in this particular scenario. Alright? And if you observe that it will be divided into 250 such blocks if you are designing in such a manner. That's all about the padding. Right? So padding basically uses the message length to alter the message length to fit in the requirement of the block ciphers. That's it. Right. So let's move on. Now a block cipher has two ways of representation. So a modern block cipher has either substitution cipher or a transposition cipher. This also we have discussed a lot in our first module, the end of first module, I would say. So if the cipher is designed as a substitution cipher, see the property, a 1 bit or a 0 bit in the plain text can be replaced by either a 0 or a 1. So 1 will be replaced by a 0 or 0 can be replaced by a 1. This means that the plain text and the cipher text can have different numbers of 1. Now the significance of this is very, very important. Although it is just a single line, but the point is, just imagine accordingly. Or rather, I'll finish off the transposition, then I'll tell you the significance of it. So, for example, a 64-bit plain text, okay, which has 12 zeros and 52 ones, can be encrypted to a cipher text with 34 zeros and 30 ones. This can be one of the possible combination. As you can see, the plain text, the number of zeros and one plain text has, and the cipher text is having, is different. Now, keep that in mind. Keeping that in mind, let's take the second one, transposition. If this is block ciphers used as a transposition, the bits are only reordered. That means the number of zeros and ones will remain as it is. So the point is here, what was the significance? I was telling you why people will be inclined on the first one and rather than the second one. Can you tell me what is the intuitive understanding that you can have from the statement that is in front of you? Which one will you choose as a ciphering technique? Given the fact that in substitution we are substituting zeros and ones alternatively, and in transposition we are reordering the zeros and ones. Which one, according to you, will suit us with respect to security aspects? Sorry? First one. Definitely first one. Why? Because in the transposition, what will happen, we know that whatever happens, you will soon find with an example, whatever happens, but the number of ones and number of zeros are the same. It won't change. So if I do a brute force attack or a frequency analysis of it, at some point of time, we might decipher the data itself. But in case of the first one, we don't know how many number of ones and zeros are there. And that's why in the cipher text, as the length is different, the number of zeros and number of ones, definitely, even if I do a brute force attack, it doesn't guarantee that the data that we are encrypting or decrypting is correct. So that's why you will soon find that most of the techniques that we are going to soon follow, they will follow with respect to substitution cipher only. Alright. So let's see about one by one. So you can see to be resistant to exhaustive search attack, the modern block cipher needs to be designed as a substitution cipher. Clear? So that's the basic idea why we are choosing mostly substitution, but we are going to discuss on transposition also to understand what is the importance of substitution, the substitution technique. In fact, so now comes to the first two cases, which I think I will finish off on this. This is one of the example I'm talking about. Suppose that we have, this is the significance of the numbers that I'm talking about. Suppose that we have a block cipher where n is equal to 64. If there are 10 numbers of ones and in the cipher text, and how many trial and error tests does Eve needs to do to recover the plain text from the intercepted cipher text? In each of the following cases. First is that it is using the cipher is designed as a substitution cipher, and the second one there substitute is a transposition cipher. Now, when you are using the substitution cipher, what is happening that Eve has no idea, as you can see, no idea on how many ones and zeros are there in the plain text. As per the rule of substitution itself. So Eve needs to try almost around 2 to the power 64, because 64 is the n equal to 64 given. So that many possible combination it has to check, and that will take, even if it takes around 1 billion blocks per second, if the processing speed is like that, it will still take hundreds of years to find out the right solution to it for a substitution cipher. Now imagine the 64 is even more, naturally the combinations will be even further, so the complexity is even more further, like complex. On the other hand, if I do the same thing for transposition, in transposition we know about that there is 10 number of ones in a cipher text. You can see exactly 10 number of block in the cipher text. So the transposition only has happened. So what we can do, we can ideally use the formula. Can anyone tell me what we are doing over there in the red color thing? Is it familiar as an equation to you? Combination form. What is the formula? Y 64 factorial divided by 10 factorial, and that NCR. Yes, that's what we are trying to do. So we are basically using, for people who have forgotten plus 12 and standard part of it. So this is the formula that we are actually going to use over here. So here what we are observing is, the important thing is that we actually can find out that by exhaustive search attack, that 64-bit blocks which are using exactly 10 number of ones, and that is coming around that 1514732148116. And suppose it has a very high speed of processing, like 1 billion tests per block, then it will only take 3 minutes to convert to check the final solution correctly. So that is the difference between a substitution and a transposition cipher, and how we are going to define, or why we are focusing more on the substitution cipher. Right? So the block cipher is what we have discussed. We have discussed about the property of it, some of the cases, how the keys have been generated, what are padding, how they are used in the system, what are the necessary of a substitution cipher over the transposition cipher. So the last thing before we end up our discussion with is where we are discussing about, with respect to transposition only, we will start with the transposition first. Again, a significance of why we are not going to use transposition is with respect to the length of key. Because key length is also very important. The more the bigger is the key size, naturally we will have more number of combinations to fit in. Right. So now please make a note of here. This is called as full size key transposition block cipher. So we need to, first we assume that, first of all, one of the first significant part is we need to know that whether the modern block cipher is a group or not, based on the property that closure, associative, and all other things. First we assume that the key is long enough. So make this long enough, we are going to use the first technique using the transposition technique. That's the transposition technique. Now what does that mean? The full size key transposition only transposes bits without changing their values. Right, that's already we have discussed. So if there is some kind of there will be a block called n object permutation. Please make a note of this. N object permutation with a set of n factorial permutation, which will give us a final result of key, which is given over here. their key length will be given as log to the base 2n factorial bits. Alright, so if it is a full size key transposition cipher, then we will have a number of bits as log of this. And there will be, and so suppose you, in the example it's mentioned over here, suppose it's a 3-bit block cipher. 3-bit block transposition cipher, to be honest. So in that case, what will happen? The permutation table will be 3 factorial, because here it's mentioned. Permutation table will be 3 factorial. So we have 6 elements. If there are 6 elements, then there are possibly the key size will be of 3-bit long only. Just remember this example carefully. 3-bit is what we are considering very simple, trivial permutation we are doing. And we have 6 possible elements. From that, we are finding out that the key length will only be of 3. So let's see here the diagram. So this is something like a scenario that we are in. So we have a 3 object permutation. So this is a predefined permutation table or a object sorter, you can say, or a mixture, you can say, because here the key size is determined with 3 bits and the possible inputs are 1, 2, 3. So the final set of elements are these 6 elements. First, understand this. Now, suppose the same thing we are doing with a substitution. In substitution, what will happen if I don't even look into other things? One very important thing is there and is there here. In case of substitution, what will happen for the full key substitution cipher? The number of key elements in the previous one was n factorial, whereas here it will be 2 to the power n factorial elements. So the number of key will be log to the base 2, 2 to the power n factorial as the key length. So you can see, I'll just give you an same example. So this is basically 2 to the power n permutation we are doing. Based on that, we are getting this 40,320. We are taking a log of this whole thing and we are getting around 16 bits. So the 3-bit, the same 3-bit block cipher which we had used for transposition, it was generating a 3-bit key. But for a substitution cipher, the same 3-bit with the combination of 2 to the power n factorial, we are generating a 16-bit combination of element. So naturally, as per the security concern, 3 bits is easy to crack. Whereas for the 16-bit, it will be really difficult to crack with all the combination possible. So that is one of the significance of, now naturally you can see 3-bit block cipher is a very trivial solution. To this point, whatever we have discussed, we were using 64-bit block ciphers. The padding examples we are talking about, 64-bit block cipher. So imagine this 3-bit is a 64. So basically you are doing 2 to the power 64 factorial as the number of elements. Can you understand what I'm talking about? Suppose this 3-bit is 64-bit, so it will be 2 to the power 64 factorial. That will be the number of elements. So you will have log of 2 to the power 64 factorial with a floor, the filling function. That will be the number of bits for the key. Now you can imagine, so how many possible combinations of key is possible? So we are securing the key in such a manner that nobody can ever decipher it so easily. Even if we get the cipher text, even if we know about the key, which possible key has been used, you should not be knowing. So that is the basic advantage of having a substitution-based block cipher instead of the transposition. Now we will see in next subsequent cases that what about this permutation? How this permutation works? This is where you will find S box, P box and certain other elements which are because for the timing this is a black box. This yellow color thing is a black box. What goes inside? Okay, keyless transmission, key transmission and all. That is the second part of the system of block ciphers. Right? So let us, I think, yeah. So this is the concluding remark for us. So please make a note of this last value of it. So transposition, the key will be of log 2 to the base n factorial to the base 2. Whereas for substitution, it will be log 2 to the power n factorial to the base 2. Naturally, it will be lot long and more secure. Alright, so this is where we are. Thank you. Just give me a